Chapter 5, Section 4.5, Part 3 video. In this problem, we're looking at the half-life of radium, excuse me, 226, and it's 1620 years. So write a decay law for radium 226 using R for the initial value. So if we look at this, we should have a sub 0 times b raised to the t. Well, they said we want to use R for the initial amount, so that takes care of the a sub 0. Now, we're looking at half-life, so the base is 1/2, but not necessarily, it could be equivalent to this, and that's what part B is going to be showing you. But if you're talking about half-life, you put 1/2. Now, how long does it take before it does its half-life? Well, that's T over 1620. So you have R times 1/2 raised to the T over 1620. So that's the initial equation. Now, what is the annual decay rate for radium 226 to the nearest thousandths of a percent? Well, this is where you're gonna, what I was talking about, equivalent base. So the base is going to be 1/2 raised to the 1 over 1620 if we want a true base that takes in account half-life over 1620 years. So if you look over here, you go 1/2 raised to the 1 divided by 1620. I think it is 1620, right? Yeah. You're going to get 0.99957. Now, it says to the nearest thousandths of percent. So let's kind of think about this. If I have to go to the nearest thousandths percent, that means I have to go to 3 decimal places after I put it as a percent. So that means when I do this calculation, I have to be out to 5 decimals. Okay, so you can hit mode and go down to float and make sure it's highlighted on 5, and then second mode to quit. So 0.99957 yeah, 3 nines. All right, so to put it as percent, 1, 2, yeah, and that would be, well, wait. Let me back up. I'm getting ahead of myself. That's the base, and base equals 1 minus R for decay. So basically, if you solve in terms of R is 1 minus B. So 1 minus 0.99957. So we'll come over here to our calculator and we'll go 1 minus second negative, which gives me the previous answer. And that's really good that it put it like that. So let me write this down. 4.27. It's really scientific notation is what they have. Okay, so if I want to move this out of scientific notation, then 1, 2, 3, 4. Okay. So R is really 0.00042778. Now, so 0.0428 would be your percent. Okay, so don't forget about this part right here. Don't jump the gun like I initially tried to. So, but it's equivalent base, and what I was preluding to up here, you know, I put it 1/2 raised to the t over 1620. That's in a correct equation. But if you truly wanted a base that you just raise it to a t to a power, then it would have to be 0.99957. So you can have equivalent bases per se. Now let's look at this one. Same thing. 1798, the English political economist Thomas R. Malthus claimed that human populations unchecked by environmental or social constraints double every 25 years. Use M for the initial population. Remember, A sub 0 times B raised to T. So they said, hey, use M for A sub 0, so times. Now, doubles, right? Doubles is 2, triple would be 3, right? So we're going to say 2. Now, it doubles every 25 years, and that's what that's raised to. Okay, so what is the growth rate in unconstrained conditions? The growth rate to the nearest hundredths of a percent. We've already got our calculator set up to 5 decimals. Let's just leave it. So we're going to say base is equal to 2 raised to the 1 to 20 over 1/25. We're going to get an answer. So let's go clear all that. 2 raised to the 1 divided by 25. Okay, and it's growing. So it's 1.02811. So, all right, now, remember base is equal to 1 plus r. So if I subtract 1, I get 0.02811, ladies and gentlemen. And then if I turn around and 1, 2, I get 2.811% for R. So to the hundredths, so 10 hundredths, so 2 decimal places, so 2.81%. Okay. Now, so the previous problem and this problem are very similar. One's a growth, one's a decay. Okay. Now let's look at this. And carbon-14 occurs in living organisms, which with a fixed ratio to a non-radioactive carbon-12. After a plant or animal dies, the carbon-14 decays into a stable carbon with a half-life of 5730. This is really the same thing. Make C be A sub 0. Half-life is 1/2. Now, 1 over 5730, because it takes 5,730 years. When samples from the Shroud of Turin was analyzed in 1998, they were found to have 91.2% of their original carbon-14. Used the decay law to answer this question. How old were those samples in 1998? Well, give your answers accurate to the nearest 10 years. So what we're looking at is, well, how much do we start with? You can start with any number, I guess. But the easiest one to start with that you would have 91.2% would be, if I done this, 1 times 1/2 raised to the 1 over 5730. The reason I'm doing 1 is that's going to be in Y1, and Y2 is going to be 0.912. That's the amount. And then we'll just solve for T, right? We'll solve for T. All right, so, and we'll do it to the nearest 10 years. So, clear, clear, clear some stuff there. All right, back up. So we're going to go 1 times, and that 1 is just there to show you initial amount, right? 1/2 raised to the x divided by 5730, and I think that's 5730. Yeah. All right, now 0.912. 0.912. How many years? Well, let's just hit graph. Let's do zoom 6. Let me look at my windows real quick. Negative 10, 10. Let's do, if it takes 5,730 years for it to half-life, then let's do minus 1,000. 5730, and we'll do it by 500. Now, the outputs are going to be from 1 down to 0. So let's think about this. So it needs to be, we could say, negative 0.5, and we could say really 1 if we want to. And then we could step it by 0.25, and then let's just hit graph. See what happens. All right, so that gave us, 5,730 years. That's what I put it out for on the x-axis, really. And then my outputs from 1 to 0, right? 1 initial amount, and then 91% of that still left. So let's go second trace, 5, enter, 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 and 761.48. So to nearest 10 years, nearest I'd say is 760. There you go. So I'll set this one up, and then I'll let y'all solve it. It's just like the one that we just got done doing. Half-life of this is C times 1/2 rate. Getting too quick on my writing. 1/2 raised to the t over 432. How will it take for 20? Yeah. Okay. So on the previous problem, they said how long will it take for 91.2% of their original carbon to still be there. On this one, it's saying how long will it take for 20% of it to decay. Well, in Y1, you're going to have 1 times, let's go ahead and put a parentheses, 1/2 t over 432, and then Y2, well, if 20% of it's to decay, well, how much is still left? 80. So you need to find out where the intersection of 0.8. And those, you can move your x, if I'd said x min, x max, I'd make 432, because it would be at 50% if it was 432, right? Does that make sense? And then I'd go, I don't know, negative 100, I guess, and then you could step it by 10 or 20, it doesn't really matter. And I'd keep my y max, y min, y max, negative 0.5, m1, and then step it by 0.25. Okay, and you can find the answer from there. nearest 10 years, right? 5 and up goes up, 4 and down stays around, right? So, okay. That concludes Chapter 5, Section 4.5, Part 3's video.